Pulmonary ventilation is adapted with the body's metabolism. How to evaluate? In exercise, why is slow, deep breath more effective than rapid, shallow breath? To settle these questions, we'll learn the assessment of pulmonary ventilation. Pulmonary ventilation can be evaluated from pulmonary volume and capacity. Tidal volume is the volume of air inspired or expired during a normal breath, about 400 to 600 milliliters at the end of inspiration. If we inspired more forcefully, we can inspire more air. It's inspiratory reserve volume, reflecting the reserve capacity of inspiration, about 3 or 4 times of tidal volume. At the end of usual expiration, if we expired more forcefully, more air is expired. That's expiratory reserve volume, reflecting the reserve capacity of expiration, about 2 times of tidal volume. The volume of air remaining in lungs after the normal forceful expiration is residual volume, 1,500 milliliters in male and 1,000 in female. At the end of usual expiration, the volume of air remaining in lungs is called functional residual volume. It can buffer the change of oxygen and carbon dioxide. After forceful inspiration, exhale as much as possible. The maximum volume exhaled is called vital capacity. It's the sum of inspiratory reserve volume, tidal volume, and expiratory reserve volume. The average in male is about 3,500 milliliters, and in female is about 2,500. It can reflect the maximum capacity of ventilation. In measuring vital capacity, the breath time isn't limited. In ventilation dysfunction, vital capacity can be normal by prolonging the breath time. At this time, we can use forced expiratory volume. After a maximum inspiration, exhale as soon as possible. The amount of air exhaled is called forced expiratory volume, also called timed vital capacity. It's usually expressed by the percentage of expiratory volume of vital capacity at the end of the first second, the second second, and the third second. FEV1, FEV2, and FEV3 of normal adults accounting for 83%, 96%, and 99% of vital capacity respectively. FEV1 was the most important in screening obstructive lung disease. Reduced FEV1 suggests obstructive damage to LV. Minute ventilation is the total volume of gas inhaled or exhaled per minute, which is the product of tidal volume and breath rate. During eupnea, minute ventilation is 6 to 9 liters per minute, which varies with age, sex, body shape, and activity. In breathing, not all the inhaled gas can exchange with the blood effectively. Dead space is the part of respiratory system with no gas exchange. The respiratory tract, with no gas exchange is called anatomical dead space, about 150 milliliters in normal adult. In upright position, the apex of lungs can't exchange with the blood. The volume of alveoli without gas exchange is called alveolar dead space. When healthy adults lie on their back, alveolar dead space disappeared. Anatomic dead space and alveolar dead space are called physiological dead space. Minute ventilation can't reflect ventilation effects due to dead space. Alveolar ventilation is the volume of fresh air inhaled to exchange with blood, equals to tidal volume minus dead space multiplied by breath rate. Anatomical dead space is constant relatively, about 150 milliliters. The change of tidal volume and breath rate have different effects on alveolar ventilation. From this figure, we can see that with the same minute ventilation, deep and slow breaths can increase alveolar ventilation, which is conducive to gas exchange. Therefore, in exercise, we should do deep and slow breaths. Next, let's do a summary. All the indicators we learned above can be applied to evaluate pulmonary ventilation. In different cases, different indicators are applied. Vital capacity and timed vital capacity are applied to differentiate obstructive and restrictive pulmonary ventilation dysfunction. In exercise, we should do deep and slow breaths to increase alveolar ventilation. That's all for this class. Thank you. See you.